Hello, good day, my dear students. Once again, Teacher Joy is back for lesson 2, which is entitled Carry Out Measurements and Calculations. While humans interpret words and pictures, computers interpret only patterns of bits. So in our next lesson, let us understand how computer interprets data and information. But before that, we will have first the objectives of this topic. Number one is identify different number systems. Second is learn how data are digitally represented in a computer's memory. And the last one is demonstrate how to convert one number system to another number system. By the way, why we should learn this topic? Why is it important to know the different number systems? As what I have mentioned earlier, that humans interpret words and pictures. Computers interpret only patterns of bits. So since computer uses a machine language and humans uses our language too, so we need to communicate with each other in a particular language made of letters or words. We normally type letters or words through keyboard of the computer, but computer does not understand the words and letters. Rather, those words and letters are translated into numbers. So this means that computers understand only numbers. So we know the decimal number system, which is based of 10, and are very comfortable with performing operations using this system. It is also important for us to understand that the decimal system is not the only system in the world. So by studying other number systems such as binary, which is base of 2, octal, base of 8, and hexadecimal, which has a base of 16 and so forth. So we will gain a better understanding of how number systems work in general. So number systems are the technique to represent numbers in the computer system architecture. Every value that you are saving or getting into from computer memory has a defined number system. So as computer architecture supports following number systems, so that is why we need to study them and also need to know the conversion technique between them. So let us have the digital representation. Information is represented and stored in digital binary format within a computer. The acronym BIT or BIT is an abbreviation of the word binary digit. Binary digit is the first two letters of the word binary is B and I, and the last letter of the word digit is T. So that is where the acronym BIT came from, and that is the smallest piece of data representation in the computer. A bit can only have two possible values, a one digit or a zero digit. One represents an on state and the zero represents an off state. So a bit can be used to represent the state of something that has two states. So let us learn first the different number systems. Let us give focus on these four number systems, the binary, octal, decimal, and hexadecimal. Let us take into consideration first their definitions. Binary numbers is a number system which ranges from 0 to 1, or it has a base of 2. Then octal numbers, a number system which ranges from 0 to 7. If you try to count numbers 0 to 7, there are 8 numbers which is included as part of octal numbers. That is why octal numbers has a base of 8. The third one is the decimal numbers, a number which ranges from 0 to 9. 0 to 9, there are 10 numbers are included in that number system. So that is why decimal numbers has a base of 10. And the last one is hexadecimal numbers. A number system which ranges from 0 to 9 and letters A to F. So if you try to count numbers 0 to 9 and A to F, A, B, C, D, E, F, there are 6 numbers, and 0 to 9 there are 10, so 10 plus 6 is 16. So meaning hexadecimal numbers are numbers that has a base of 16. So this time, we will learn how to convert decimal numbers to binary numbers. We will have to start from decimal to binary because this is the numbers that we are using daily, the decimal number system. This is based on our 10 fingers. So converting decimal numbers to binary, all you have to do is to divide the given decimal number by 2. So 2 is a constant number or a constant divisor because of uh, the decimal number is being converted to binary number. So that is why your divisor is a constant, which is 2. Then get the quotient and the remainder of those numbers. Then bring down the quotient and divide it by 2 again and get the quotient and remainder again. So you need to do it repeatedly until the quotient results to 0. Copy the remainder from bottom to top, and that is the binary equivalent. So let us take into consideration this example. So we have here 30 decimal number system. So first, you have to place two columns, one for the quotient column and for another column is for the remainder column. So let us start dividing. 30 divided by 2 is equal to 15, and you have to place it under the quotient column. And when you multiply 15 by 2, that is 30. So therefore, the remainder is 0. And the 0 remainder is, you have to place it under the remainder column. Then the last quotient is 15. So therefore, you need to repeatedly doing division process until the quotient becomes 0. So since our divisor is still 15, therefore we still have to divide repeatedly. So 15 divided by 2 is 7, then remainder 1. Then again, 7 divided by 2 is equal to 3, remainder 1. Then again, 3 divided by 2 is equal to 1, remainder 1. And 1 divided by 2 is equal to 0. So take note, the quotient is now 0. So therefore, 1 divided by 2 is equal to 0, and it has a remainder of 1. So we will have to terminate the division process because the quotient becomes 0 already. Therefore, that ends the process. So how to get the answer for, or the equivalent for 30 decimal number system to binary is that you have to read the remainder from bottom to top. So this time, the remainder is equal to 11110. And that is the binary equivalent of 30 in decimal. So that is base 2. So in checking, you have to check your work because this is mathematics. We can actually check our the result. So you have to write 11110 as our multiplier equivalence. Then those numbers written 11110, you have to place under that, you have to place 1, 2, 4, 8, 16. So that number is being multiplied by 2 to the exponent of starting 0. So from right, the first exponent is 2 to the power of 0, then 2 to the power of 1, 2 to the power of 2, 3, 4, and so on and so forth. So this time, it is being summarized. Those exponential formats is being summarized, and that results to 1, 2, 4, 8, 16. So meaning the multiplier equivalence is being multiplied by 2. Whatever the last digit will be multiplied by 2. So if ever there are still additional digits to the left, after 16, you need to multiply 16 by 2, and that will result to 32. So this time, you have to add all those multiplier equivalents, those under ones. But for the zero, that would be zero because you have to multiply that by uh, those numbers. So 1 times 16 is 16, 1 times 8 is 8, 1 times 4 is 4, 1 times 2 is 2, 0 times 1 is 0. Then add all of them. So you need to add 16, 8 plus 4 plus 2, and that results to 30. So meaning binary digits 11110 is really equal to 30 in decimal. So that is just a reverse process in order to check your work. So let us take into consideration another example. We have here 125 in decimal. Again, you have to divide 125 by 2, and that is 62, remainder 1. So one thing you should have to put into your mind when you have to divide, when you have to get the remainder is that the remainder should always be 1 if the number being divided by 2 is an odd number, and you have a remainder of 0 when the number is even number, because our divisor is 2 and that is an even number. So I'll repeat, if you have to divide that number by 2, that odd number by 2, the remainder is 1. And if that is even number to be divided by 2, the remainder becomes 0. So I'll repeat, 125 in decimal, what is that equivalent in binary? So we have here 125 divided by 2 is 62, then the remainder is 1, of course, because 125 is an odd number. Then the last quotient is 62. So that 62 na po, that would be divided by 2. And that results to 31. So since 62 is um, an even number, therefore the remainder is 0. So the last quotient is 31. Again, still, since our quotient does not reach yet 0, so we still have to uh, repeatedly perform the division process until the quotient becomes 0. Until 1 divided by 2 is equal to 0, and that's having a remainder of 1 because 1 is an odd number. Therefore, that ends the process of division. Therefore, reading the answer upward, that results to 111101 in binary. That is the equivalent value of 125. So let us try to check that 111101 in binary to be converted back or reverse, or the reciprocal of that number is 125. Let us check if that is really equal to that 125 in decimal. So again, you have to write the multiplier equivalence, which is 1, 2, 4, 8, 16, 32, 64. If you have noticed, with the previous example, this one, the last digit is 16 in the multiplier equivalence is 16. So this time, we added 32 and 64 because there is an additional digits of 1. Again, bring down 64 and 32, 16, 8, 4, or those numbers or multiplier equivalents which is under 1. And for those 0, so you need to cancel that one because the value is still 0. Then for the last one is 1. Then sum them up, all of them, 64, 32, 16, 8, 4, and 1, and that will result to 125, which is the decimal equivalent of 111101. So I hope you learn from this conversion from decimal to binary, and the checking is that conversion is from binary to decimal. So let's proceed to conversion of octal numbers to binary. Um, Let us take into consideration that octal numbers ranges from 0 to 7 and it has a base of 8. So in the first example, we have here 54. So meaning if the conversion is in octal to binary, you should always mind that there is no number which is 8 under octal number system because octal is only from 0 to 7. So you can repeatedly write 777, 357, but not that you have to use digits which is greater than 7 because I'll repeat, octal numbers is from 0 to 7. Okay, so the first example here is 54 base 8 is equal to blank in binary, which is base of 2. So the process is you have to write them separately. You have to write 5 and 4 because you have to give a 3-digit value or 3-digit binary equivalent in every octal number, in every given octal number. So we have here 5. Again, to get the binary equivalent is that you have to use the multiplier equivalence, which is 1, 2, 4, since there are only 3 digits. And 1, 2, 4, you can no longer use 1, 2, 4, 8, 16, 32 because in every octal number, there is only assigned 3 digits. So 1, 2, 4, if you try to add, if ever all the 3 digits is 1, if you add 4, 2, and 1, that is already 7. So meaning there is no greater value than 7. So we have here, so 5, you should have to look at where you can find a sum of 5. So from out of 1 to 4, you have to consider where to get a sum of 5. So meaning 4 and 1, that is equal to 5. So therefore, under 4 and under 1, you have to write 1. And for the digits 2, you have to place it 0 so that when you multiply 2 by 0, that will result to 0. Then add 4 and 1, that is equal to 5. Then since the given is 54, so the digits no 4, again, you have to assign 1 to 4. So since it is 4, so ang 4 maoy 1. Therefore, the rest of the multiplier equivalents, 2 and 1, should be written with 0. So therefore, the binary equivalent of 54 is equal to 101. 101 is equivalent to 5, and 100 is equivalent to 4. So putting them together, 101, 100, that is equivalent to 54 in octal, and that's the binary equivalent of it. Okay, so next example is 16. 16 in octal number, converted to binary. Again, you have to separately write 1 and 6. So out of, even if the value is only 1, you should have to write them uh, in 3-digit form. So 1 could be written only by 001. So even if the value is only 1. Then for 6, we have 4 and 2 that composes 6. Nga kanang 1, that should be 0. So that when you multiply 4 by 1, 2 by 1, that results to 6. When you add all their products. Okay. So the binary equivalent of 16 in octal is 001 110. So that's it. Then converting binary numbers to octal. So this is just the checking of the previous conversion. So we will use the result in the previous example, the result of 54 and the result of 16, so that we can check our work whether the binary equivalence as the result of the given numbers in octal are really correct. So we have here 101, 100 in binary is supposedly to be converted to octal numbers. So again, so for this time, 101, 100, you have to assign that 1, 2, 4 in every digit. So tanang-tanang na 1, that should be multiplied by the multiplier equivalence. So meaning 1 times 4 is equal to 4, 0 times 2 is equal to 0, then 1 times 1 is equal to 1. Then you have to add them up. That results to 5. So that is the first digit of your answer in octal. Then the next number is 100. Again, 124, you have to write the multiplier equivalence, 124. So 1 times 4 is equal to 4, 0 times 2 is equal to 0, 0 times 1 is equal to 0. Then total them up, 4 plus 0 is equal to 4. Therefore, the first digit is 5 and the second digit in the octal equivalent is 4. Therefore, 101, 100 in binary is equal to 54 in octal. So next is 001, 110 in binary to be converted in octal number. Again, the first 3 digits of the binary equivalent is 001. So you have again to write the multiplier equivalence, which is 124. Uh, 0 times 4 is 0, 0 times 2 is 0, 1 times 1 is 1. Then add them up, that results to 1. And that represents the first digit of the octal equivalent. Then we still need to get the equivalent of the second group, which is 110. So write again below the 110, the binary multiplier equivalence, which is 124. Again, multiply 1 by 4, 1 by 2, and 0 by 1. That is equal to 4 plus 2 plus 0 equals 6. Therefore, the octal the binary equivalent of uh, 001 is equivalent to 16 in octal. Okay, so let us have the last one. Converting hexadecimal numbers to binary numbers. I think this is more complicated than the previous two number systems because hexadecimal numbers includes the following. It includes numbers from 0 to 9, and it also includes letters from A to F, where A is equal to 10, so meaning the continuation of number 9. So instead of writing 10, you are not allowed to use any more 10, but rather it should be A. Then 11, B is equal to 11, C is equal to 12, D is equal to 13, E is equal to 14, and F is equal to 15. So I'll repeat, instead of using 10, 11, 12, 13, 14, 15 as the equivalent in hexadecimal, do not use them anymore, but rather use their letter equivalents of those respective numbers. Okay, let's proceed. Um, we have here hexadecimal numbers is a number system with a base of 16. So we have to convert that number to binary numbers, which is of base 2. So number 1 given is 1F. 1F base 16 because we are converting hexadecimal numbers to binary numbers. Again, in every hexadecimal number, it should be represented by 4 digits in binary. And we will use again the multiplier equivalence, and this time it is up to 8 already, not anymore 1 to 4, because 1 to 4 is for octal, because octal is has only 3 digits equivalent in every one octal number. So this time, since this is hexadecimal, so you have to use um, 1 to 4 as the 1 to 4 8 as the multiplier equivalence, because whenever you have to add 8 plus 4 is 12, plus 2 is 14, plus 1 is 15. And that is the highest number in hexadecimal. So therefore, that is why we are using 1248 as our multiplier equivalence. So going back to the first given number, which is 1F, so again, you have to write them separately, 1 and letter F. So for 1, again, you have to write the multiplier equivalence, which is 1, 2, 4. And since it is only 1, you have to look for a number. When you add, it will result only to 1. So therefore, under 8, it should be a 0. And for 4, that should be 0. And for under 2, that should be 0. And 1, that's the only digit that you have to write the 1. So that when you multiply 1 times 1 is equal to 1, and the rest is 0. When you sum them up, it will only give you the result of 1. So that is for the first digit of the hexadecimal number that is given. So for the second digit, letter F. So letter F is, I'll repeat, this is equal to 15 based on the given equivalence in the previous slide. So we have, since this is 15, so if you try to add 8 plus 4 plus 2 plus 1, if you multiply them, all of them by 1 in each digit, it will result to 15. So 8 plus times 1 is 8, 4 times 1 is 4, 2 times 1 is 2, 1 times 1 is 1, and you have to add all those products, 8 plus 4 plus 2 plus 1, that is equivalent to 15. So therefore, 1F in hexadecimal, which is base 16, is equal to 0,001,1111 base 2. So that's it. Okay, let's have another example so that you will uh, internalize the discussion. Let us give another example. So we have here bed, B-E-D, base 16, meaning bed in hexadecimal to be converted in binary, which is base 2. So again, you have to write those three letters or three-digit letters separately. B separate from E and D separated from B and E. So you have to write also the multiplier equivalence, which is 1248, 1248, 1248. Then uh, just try to imagine out of 1248 multiplier equivalence where you can get the value of the given hexadecimal. So as of this time, B is 11, E is 14, and D is 13. So therefore, to get 11 out of the multiplier equivalence, so you need to have 8 plus 2 plus 1. And that will result to 11 or equivalent to B. So therefore, the binary equivalent is ang 8 mo mo 1, ang 4 mahimong 0, so that when you multiply 4 by 0, that is 0, then 2 and 1. And that will result to 11, which is equal to B. Then for the next digit, E, 8 plus 4 plus 2, that is 14. So E is equivalent to 14. Then the last one is letter D. D is 13. So you can have a sum of 13 when you add 8 plus 4 is 12 plus 1. So that is equivalent to 13. Therefore, the binary equivalent of bed in hexadecimal is 1011 1110 1101 base 2. So those are all the conversion process of the different number system. So let's proceed to calculating data storage. While a bit is the smallest representation of data, the most basic unit of digital storage is the byte. A byte is equivalent to 8 bits. So meaning if you have 2 bytes, meaning it is equal to 16 bits. And is the smallest unit of measure or UOM, unit of measure, used to represent data storage capacity. When referring to storage space, we use the terms bytes, kilobytes, or KB, megabytes, or MB, gigabytes, GB, and terabytes, TB. So 1 kilobyte is a little more than 1,000 bytes. So specifically 1,024 bytes. That is equivalent to 1 kilobyte. A megabyte represents more than a million bytes or 1,048,576 kilobytes. That is equivalent to 1 megabyte. A gigabyte is, giga means billion. So 1,073,741,824 bytes. Then the last one is the terabyte. So a terabyte is equivalent to trillion bytes. So 1,099,511,627,776 bytes. So those are the basic equivalents of the different data storage. Here is another conversion. So just recently, we have discussed about the different number systems, conversion of number systems. So this time, we have here the conversion of the data storage. So 1 byte is equivalent to 8 bits. 1 kilobyte is 1,024 bytes, and 1 megabyte is 1,024 kilobytes. 1 gigabyte is 1,024 megabytes, and 1 terabyte is 1,024 gigabyte. So this is the very basic equivalent of the data storage. Examples of components and devices that use bytes includes the following. Number one is RAM, hard disk drive space, CDs, DVDs, or BDs. These are, um, in general, these are called as optical drives. CDs have a data storage capacity of approximately 700 MB. So what is that 700 MB? 700 megabytes. Then DVD have a data storage capacity of approximately 4.3 gigs or gigabytes on a single layer disk and approximately 8.5 gigabytes on a dual layer disk. Then for the Blu-ray disc or BDs, have a storage capacity of 25 gig on a single layer disk and twice if it is uh, twice of the single layer, which is 50 gigabyte on a dual layer disk. Okay, we have here examples. There are only two. I'm preparing two examples for this conversion. How many bytes does a 25 kilobyte file have? Let us take into consideration that 1 kilobyte is equivalent to 1024 bytes. So therefore, 1024 bytes is equal to 1 kilobyte. So that is 1024 bytes over 1 kilobyte, or that is the ratio. 124 bytes is equal to 1 kilobyte. Then multiplied to 25 kilobytes because the question in the problem is how many bytes does a 25 kilobyte file have? Therefore, so if you have just noticed, the key is being concealed. Therefore, the remaining units is only bytes. So 1024 bytes times 25, that is 25,600 bytes in a 25 kilobyte file. Okay, so second example, if this 25 kilobyte file is stored in a 1 MB folder, so the previous example is 25 kilobyte, and that is equivalent to 25,600 bytes. Diba? In the previous example, it is equivalent to 25,600 bytes. How many files can be stored in that folder if every file consists of 25 kilobyte? So please take note that 1 MB is equivalent to 1,000 for 1,048,576 bytes. And just recently in the computations of the 25 kilobyte, that is equivalent to 25,600 bytes. Therefore, uh, 1,048,576 bytes divided by 25,600 bytes, and that results to 40.96 files can be stored in a 1 MB folder. So based on the result of the calculator, when you divide 1,048,576 divided by 25,600, and that results to 40.96 files. So there are 40.96 files that can be stored in a 1 MB folder if each file consists of 25 kilobytes. Okay, so those are the very basic conversion of the data storage.